Hello, welcome to this video. My name is Wuyang Chung. The title of this video is Using Segmentation to Build a Capability-Based Single Address Space Operating System. This video will talk about three old technologies, that is segmentation, capability, and a single address space operating system. These three technologies are actually related to each other. By combining the three together, we can build a system that's more secure and more efficient. Here is the outline of this video. First, I'll talk about the advantages of single address space operating system. Then I'll talk about the capability-based addressing, because capability-based addressing can actually be used to build a single address space operating system. Here I'll briefly describe what is capability, and then there are two ways to build a capability system. Then I'll propose a new segmentation hardware that can be used to build a capability-based addressing system. Following that, I'll talk about a lot of benefits we can get from segmentation. Then I'll talk about how the old programs can run in this new system. And finally, the conclusion. Most operating systems today use virtual address space to protect processes from each other. That is, each process has its own private virtual address space, and so the system actually has multiple address space. The problems with multiple address space is that, first, pointers cannot be used in shared buffer because it is sometimes impossible to map the shared buffer at the same address for all the sharing processes. And second is that on CPUs that do not support address space ID, operating system will need to flush TLB when doing address space switch, and flush TLB is bad because the CPU will eventually need to reload the TLB entry from page table again. That's why most CPU today support ASID. But with ASID, there will be duplications of translation information in TLB. For example, most programs today will link with shared library. So when you run 10 programs at the same time, there will be 10 copies of virtual to physical translation for the shared library in the TLB. And a single address space operating system can solve all the problems above, but the biggest problem with single address space OS is protection. That is, how do you protect processes from each other on a single address space? There are already several methods that can be used to protect processes from each other on a single address space, such as domain page model, page group model, and capability-based addressing. In my opinion, I think that capability-based addressing is the most elegant way to protect processes from each other on a single address space. In a capability system, capability is like a key. Each object has a lock, so a program can access an object if it has the key to that object. That is, if it has the capability to that object. Capability by definition is permissions plus a unique object ID. The permissions here are the read, write, execute permissions for the object. And the object can be any object in the system, such as the process object, the thread object, the file object, or a segment. And in capability-based addressing, capability is only used to control access to segment. So the unique object ID here becomes unique segment ID. The most important thing in a capability system is to prevent capability from being forged. There are two approaches to do that: the tagged approach and the partitioned approach. In tagged approach, each memory word has a tag bit associated with it. If the data stored in the memory word is a capability, the tag bit will be set to 1. Otherwise, it will be set to 0. So, if a program tries to write a regular data to a memory word that previously has a capability stored in it, the hardware will then set the tag bit to 0. This is how the tagged approach prevent capability from being forged. In partitioned approach, a segment can store either regular data or capability, but not both. So if the program tries to write a regular data to a segment that can only store capability, it will trigger a fault. That is how the partitioned approach prevent capability from being forged. On the right hand side, the picture shows the partitioned approach. In partitioned approach, each process will have a capability list. Capability list stores a list of capabilities the process owns. And since capability is used to control the access to segment, so capability list actually stores a list of segments the process can access. From this picture, you can see that although process 0 and process 1 run on the same address space, they are protected from each other. If they want to share a segment, they will both have a capability that point to this segment. There are many ways to combine segmentation and paging in a system. In the proposed hardware, the segmentation is overlaid on top of paging. That is, the logical address is first translated to virtual address by segmentation, and the virtual address is then translated to physical address by paging. In the proposed segmentation hardware, the system have a segment metadata table. All the segments in the system will have an entry in this table. It stores the base address size of the segment along with some attributes. And each process has a capability table. Capability table stores a list of capabilities the process owns. And capability by definition is permissions plus a unique segment ID. And since each segment in the system will have an entry in this table, so the index to this table can be seen as the unique segment ID. So here the unique segment ID becomes an index to the segment metadata table. And both in capability and segment metadata, there is a tag field. The tag field is used for capability revocation. The capability is valid only when the tag field in capability is equal to the tag field in the metadata. So when the operating system wants to revoke all the capabilities that point to this segment, it can simply change the tag field in the metadata. Then all the capability that point to this segment will be revoked. So these tables are all in the kernel address space. On the CPU side, the CPU uses capability descriptor to access segment. So the capability descriptor is very similar to file descriptor. In Unix, a process can access file if it has a file descriptor to that file, and file descriptor is actually a index to process file table, and each entry in the process file table has a pointer to the v0 or i0. So in this segmentation hardware, the capability descriptor is actually an index to the capability table, and the capability table has a pointer to the segment metadata table. So there is also a tag field in the capability descriptor, and the capability descriptor is valid only when the tag field in the descriptor is equal to the tag field in the capability. And when the CPU want to access a segment, it need to provide a capability descriptor to the MMU, and if the program does not specify a capability descriptor, the CPU will then use the default capability descriptor. A program has 3 default segments, that is the code segment, data segment, and stack segment. So the process will have 3 default capability descriptors, that is the code, data, and stack capability descriptor. And capability descriptor is actually a regular data, so it can be stored in general purpose register. So the CPU will reserve 3 general purpose registers to store the default capability descriptors. In this picture, you can see that both process 0 and process 1 has the code capability descriptor point to the same segment. It either means that they are running the same program or they are currently running the same shared library. In order to speed up the segmentation translation, the CPU will have a new look-aside buffer called segment look-aside buffer, so that given a capability descriptor along with the protection domain ID of the process, the CPU can quickly know the base address and size of the segment, and also the permissions it has for the segment. And the green part comes from the capability, and the blue part comes from the segment metadata. Segment types. Segmentation translates logical address to linear address. The definition of logical address is capability descriptor plus an offset within the segment. And since there are 3 types of linear address, there are 3 types of segment. The 3 types of linear address are virtual address, physical address, and IO address. So the 3 types of segment are virtual segment, physical segment, and IO segment. For virtual segment, segmentation translates the logical address to virtual address, and for physical segment, it translates it to physical address, and for IO segment, it translates it to IO address. Now let's move on to see the benefits we can get from different kinds of segment. Let's first look at virtual segment. Virtual segment can make segment move very fast because we don't need to copy the segment data. We only need to copy the virtual to physical mapping. And second, that we don't need to fix any pointers in the segment after the segment is moved. This is because that segment always starts with 0, so we don't need to fix any pointers. And the second point actually also applies to physical segment, but usually we don't want to move physical segment, because when moving physical segment, we need to actually copy the data. And for IO segment, it is usually cannot be moved. Now let's see the second benefit of virtual segment. Virtual segment can make the page table walk in guest virtual machine more simple. Here in this picture, it shows that when a TLB miss happened in the guest machine, CPU will have to first translate the guest virtual address to guest physical address, and since the guest physical address is actually system virtual address, so the CPU will then need to translate again from system virtual address to system physical address. And with virtual segment, the segmentation can translate the guest logical address directly to system virtual address, so that when TLB miss happened in the guest machine, the CPU only need to translate from system virtual address to system physical address. You might wonder how this is possible, and this is because that this is because that it only happens in pair virtualization. In pair virtualization, the guest OS actually do not have any virtual memory management code, and when the guest OS want to create a segment, it sends a request to hypervisor. Hypervisor then create the segment for the guest OS and return a capability back to guest OS. So the capability in the guest OS actually pointing to the segment metadata table in the hypervisor. So actually the system has one and only one segment metadata table in the hypervisor, and all the capabilities in the system, including the capabilities in the guest OS, all pointing to this one and only one segment metadata table. That is why the segmentation can translate guest logical address directly to system virtual address. Now let's see the benefits of physical segments. Physical segment can be used to implement software-managed TLB. In software-managed TLB, the TLB miss is handled by the OS. So when the OS is running the TLB miss handling routine, it must be guaranteed that no TLB miss exceptions will happen during this time. And by putting the TLB miss handling routine in physical segment, it can be guaranteed. Second, physical segment can be used as direct segment. In a paper published in ISCA 2013, they found out that for some applications with very big memory data, when those program runs, the CPU will spend over 50% of the time doing TLB miss handling, and so they proposed an idea called direct segment. That is, when the virtual address falls within a predefined range, the CPU will not use TLB. Instead, it will use simple arithmetic addition and subtraction to translate virtual address directly to physical address. And this is exactly what physical segment do. Physical segment translate the logical address directly to physical address and bypass the TLB. The third benefit is that it can make IOMMU simple. The primary two jobs for IOMMU are authorization and page translation. With capability, authorization is very simple because in a capability system, we don't care who you are, we don't care how you get the capability. As long as you have the capability, you can access the segment. And since it's physical segment, so no page translation is needed. So with capability and physical segment, IOMMU is simply a cache for physical segment descriptors. Now let's see in more detail about how the IOMMU protects main memory from hardware device. Before the hardware device can do DMA to main memory, device driver must first allocate a physical segment and sends the capability of that segment to hardware device. So when hardware device want to do DMA to main memory, it can sense the capability it gets from the hardware driver, from the device driver, and the offset and data length to IOMMU. IOMMU will then verify that the capability is valid. That is by checking the tag field in the capability and the tag field in the metadata. And it will also make sure that the capability is pointing to a physical segment. And then IOMMU will check that the offset and length is within segment size. If all the tests are passed, then IOMMU will calculate the physical address by adding the segment base address and the offset. The calculated physical address is then used to access the system main memory. Actually, this is very similar to what MMU do when CPU want to access main memory. The difference is that IOMMU only accepts capabilities that point to physical segment. IO segment. The purpose of IO segment is to leave memory address space to memory only and move all the other stuff to IO address space, such as CPU, CS control, and status register, PCI configuration space, video frame buffer, boot ROM, etc. And the benefits of I/O segment is that no memory holes will in the memory address space, and segment is more fine-grained than page because it can be as small as 1 byte. And for a large I/O buffer, only one SLB entry is needed. If using the paging to access the large I/O buffer, it will then need several TLB entries. And the send load instruction can be used to load from either I/O or memory address space. So we don't need two sets of instructions. We only need one set. So even when the device driver runs at the user level, it can access its hardware device without kernel intervention. Actually, this is the benefit of capability. In a capability system, we don't care who you are. We don't care how you get the capability. As long as you have the capability, you can access the I/O segment wherever you are, even at the user level. Now let's see how segmentation can make the implementation of shared library more simple. Traditionally, when we compile a shared library, we must compile it in PIC mode. And when the program wants to access shared library's global data, compiler must use GOT. And when the program wants to call shared library's function, compiler must use PLT. This is because that the compiler cannot know where the shared library will be loaded at runtime. That's why it needs the above techniques. And with segmentation, shared library will have its own code and data segments, and segments always starts with offset 0. It means that the offset part of all the shared library's global symbols are known at compile time, and it can even be linked at compile time. And we only need to link the capability part of the shared library's global symbols at program load time. Now let's see cross-process call. Cross-process call means that we want to call a function in another process, and the cross-process call has many names. It is also known as cross-domain call, migrating thread model, protected control transfer, and passive object model. And traditionally thread is confined into protection domains. That is the process that created it and the kernel. And when the thread is in the kernel mode, it can only return back to its creator process. If a system support cross-process call, and when the thread is in the kernel, it is allowed to upcode into other process. And the benefits of cross-process call is that it encourages modularity and improve security, and resource accounting can be made more accurate. For example, the CPU time can be charged to the correct thread, and it is preferable for real-time systems. For example, a real-time thread, when migrated to another process, it is still a real-time thread. Now let's see how segmentation can make cross-process call more simple. Traditionally, if an OS support cross-process call, it will need two stacks, one in the client process and one in the server process, to do the cross-process call. It is because that the OS want to protect the client stack from server and the server stack from client. But we can use one stack if we can use only one stack in cross-process call if we can protect the server part of the stack from client and protect the client part of the stack from server. With segmentation, it is very simple to protect the server part of the stack from client by simply moving the stack capability from client process to server process. Since the capability is moved, the client can no longer access the stack. And to protect the client part of the stack from the server, we only need a new privileged register called the stack boundary pointer register. This register point at the boundary at the stack boundary between the client process and the server process, and the CPU restricts that a thread can only access the server part of the stack. Compatibility with all programs. It is simple to maintain compatibility with all programs if the programs are 32 bits and the virtual address space is 64 bits. We divide the virtual address space into two parts. The first half of the virtual address space is reserved for kernel, subsystems, device drivers, and single address space programs. The second half of the virtual address space is divided into multiple 4 GB segments, and the old program is loaded into one of the 4 GB segment. By doing so, segmentation can not only maintain compatibility with all programs, it can also transform the old multiple address space programs onto a single address space. Conclusion: there are lots of benefits we can get from single address space capability and segmentation, but there are also lots of changes we need to make. In OS, we need to support segment capability and single address space. In compiler, we need to support file pointer, file function call, and a new shared library implementation. And in hardware, we also need to support capability and segmentation architecture. So that's all I have about this video. Thank you for your time.